few seconds just in case there's any ads playing before I get stuck in to what this video is about. And this is a part 2. So the purpose of these streams is to record the process that goes into making one of my YouTube videos. And I've got a new camera up here today, so that seems to be working just fine. And that allows me to use my better camera for the image processing side. So I want to make a video for YouTube called 8 Bits of Image Processing You Should Know. And this is part 2. So we did 4 of the bits yesterday. Well, at least we started working on the code. And the point of these streams is not to be like the YouTube videos. It's more to be like a little bit of a documentary as to what the thought process is, how I go through the code, how I tidy it all up. The things, the steps and the thought processes necessary that I go through before getting to the final video and the code. And my intention is to live stream every part of the development of this particular video project, including at the end will be the videoing and editing, although I'm not quite sure how I'm going to set that up yet. And I made a promise that I wouldn't change the code in any way, shape or form between the live streams, and that's exactly what we've got here. This is precisely where we left off. You feel that the name is a bit misleading. Yes, I suppose it does. Yes, there's definitely more than 8 bits of information on this screen. And so I'm going to carry on. Oh, hang on, let me just stop my little side stream here. And I'm going to carry on. And we left yesterday, so let me just see if this all still works. We left yesterday looking at, we were trying to do binary erosion. And obviously my brain had run out of steam and it wasn't working quite right. So I did have a bit of a think about it. And the plan was we were going to go through all of the thresholded pixels in the array, look at their sum, and make some decisions based on the sums of the neighbours of a particular pixel. So if the activity for a said pixel is 1 and its neighbour's sum was greater than 0, then I set myself to 0. And that wasn't quite working. And the reason being is we needed to change this condition. It's actually, we want to get rid of the pixel if it's got all of its neighbours. So in this case, if the sum was equal to... let me get this right, so I have to think about this. I think it's if the sum is less than 4. So if any of my neighbours are missing, then I disappear too. And that looks a bit better. And the purpose of this transformation is to sort of solidify blobs together. So on the left-hand side, we've got my thresholded image. Oh, hi, Sistran. On the left-hand side, we've got my thresholded image, which has quite a bit of per pixel noise in it. And on the right-hand side, we've started to get rid of the individual pixel noise and solidify the object. Now, it still doesn't look much better, and you might be thinking, well, what purpose does this serve? Well, we can do a few things. If we decide to dilate the image first, so I'm going to bring in our dilation code. Now, if you remember, this takes the binary threshold and then expands it outwards. So any white pixels, the neighbours get set to white too. So I'm going to do 3 levels of dilation and then 3 levels of erosion. So any single pixels will start to disappear. Let's have a look at see what this looks like. And it sort of pops in and out of view because my webcam's got an auto gain adjust. So the image on the left is just the thresholded image, and the image on the right is now a more solid image representing the objects. It's never perfect, and that's the thing with image processing, is there's often scope for things to go wrong. So we can use dilation and erosion as sort of a spatial filtering system, but in the binary domain. And there's other interesting things we can do, because what we've actually started here is the process of what's called binary morphological operations, and I hinted at that yesterday. And it's a method of applying a variety of techniques to an image. One particular technique that's worth applying, let me just comment this back out again, and I don't know if this I'll include this sort of information in the 8 bits video. Can you display FPS? Yeah, it should be displaying. It should be 30 frames per second, I think. So one of the things we can do is, once we've got a condition like this, we can change the nature of what it's being tested on. So instead of looking for if I've got any neighbours that are black, I set myself to black. What if all of my neighbours, if my pixel, if I myself am illuminated, and all of my neighbours are illuminated, then I set myself to black. Can anybody have a guess at what the end result is going to be? And this is quite an interesting one. You'll use this a fair bit when doing things like procedural dungeon generation, that sort of thing. And the result is quite nice. You end up with a very crisp digital edge detect. Now, we will look at other edge detect bits as part of the 8 bits. Now, if I bring in my test piece here, so you can see we've now got a very precise single pixel wide edge detect, and that's quite a nice thing. So look at that. There's a really nice effect. You don't get any of the L-shaped pixels either. So if you're familiar with line drawing algorithms, you can sometimes get little clusters of pixels on the diagonals, but here you don't get that. Now we got Lucas. Hey, Lucas. Yeah, so Tutus, you weren't in the stream yesterday. The purpose of these 8 bits of image processing, people think, oh, it's image processing, I'm never going to use that. The reality is you can actually really exploit image processing in game development, particularly when working with things like procedural generation and obviously the graphical things like texturing, etc. But I use it sometimes just to sort of condition data in an array to look what I want it to look like. So we all know it's quite easy to generate blobs to make dungeons, but then if you wanted to turn those blobs into walls for a particular cell, this is one potential way to go about doing it. And so we've very easily created a binary edge detect system. I'm sort of waving this around because it highlights quite nicely the effect. And when the camera starts to zoom in and focus, you can see you can actually get it. I'm probably a bit too close there. It's quite nice. And we've still got a bit of noise in the background, and so some of the other bits that we've looked at, we can probably filter some of that out. Right, so that is the start of looking at these morphological techniques. And morphological means we're going to be changing things in space, effectively using set mathematics. I don't really want to bog the video down talking about mathematics. What else can we think of when I'm thinking of morphological operations? Right, we've done it using 4 neighbour connectivity, but sometimes you might want to do things using 8 neighbour connectivity. So I'm going to bring in the dilation again. Dilation and erosion are sort of the same thing, but one's the opposite of the other. But I'm also going to, for every lit pixel, I'm going to illuminate all 8 neighbours of that pixel now. So I'm going to take that code and carefully think about how to do this. So that's going to be a -1, and that's going to be a +1. So I've added you've got the cardinal points up here, so I'm now adding the diagonals. So that's, well, it doesn't really matter what the order is, as long as we've got them opposite signs. And so that's going to do 3 levels of dilation, and we'll put this back to erosion mode. So if I'm missing a neighbour, then I set myself to 0, and just see how that tidies up the digital image that we started with. Wait for the auto gain to kick in, and that's a bit tidier than it was before. I could probably do with a higher contrast background in this particular setup. So maybe for the video I need to think about what am I actually showing. So even though my hand, you can see around the edge here, I have sort of hairy arms, and it generates texture. And one of the ways we've managed to eradicate that texture is by using this opening and closing technique, this dilation and then erode. So I've turned my hand into a solid object, really. Again, we're working with real world data, so you do get noise and pixels and things that are going on. But that's a nice way of tidying up the edges of something you've generated which is a bit noisy. Yeah, it's quite pleasing, that. You will get these little diamond effects, and the diamond effects here are caused because we're only using 4 neighbour connectivity in our erosion stages. So, is there then an 8-way equivalent of the erosion? Well, there is, so we'll try that and see what it looks like. So here we're looking for a sum less than 4, but we're only looking at our 4 immediate neighbours. Well, exactly, Tutors. I think that's this is what's quite interesting about it. It's really just working with data in 2D arrays, image processing, but there's just interesting techniques that one discipline can pass on to the other. So here I've got the addition of my 4 pixels neighbours values. I'm going to add in another 4 for the diagonals, and we'll see what this looks like. Now, I'm already aware that this particular bit is probably going to go over the 3 or 4 minute threshold. Oh, excuse me, I'm currently drinking lots of coffee. Definitely no product placement going on here, just a regular normal mug. Definitely probably won't ever be for sale, but you know, I'll just keep pointing at this and keep it on the camera for a bit. So we want to look at our immediate neighbours now with 8-way connectivity. So again, I'll just put in these diagonals. So that was an... Oh, I'll make sure I get these in the right order. That was a minus and a plus. And that one's a... Well, we'll put in a minus and a plus. So now we're summing up all 8 neighbours. So I need to change the value of my sum here to 8, because my neighbours' values are going to be 1 or 0. And we're doing that for dilation, and we'll do that for erosion, and maybe we'll get a slightly rounder image. But because I'm now doing more changes on the image, yeah, so that's kind of brought in some of the rounder edges again. A little bit strange sort of diagonal behaviour going on there. I wonder if we're suffering from what we suffered from yesterday when we were getting that triangle effect. Where's my sort of high contrast test card? So large areas remain more or less intact, although it starts to smooth the edges off. So it's sort of a rounding algorithm. So whereas we've got these harsh edges on the left, yeah, we've definitely got something going on there that's a bit strange, because it looks like we've got a bias towards the diagonals. Let me just have a quick look at the code as to why that's the case. I've probably missed something fairly obvious out with the sums. Ah, yes, I can see why. I've got 2 which are the same here. So that needs to be... we've got minus, minus, plus, plus. So we want... we've got minus, minus, and plus, plus. So we want those to be at least 1 that way round and 1 that way round, I think. So we weren't looking quite at 8-way connectivity. Let's have another look. Ah, that's looking a little bit better, is it? Yeah, so we're getting rounded edges, more or less rounded edges. It depends on the size of the shape that we're implementing. So we've added curvature to what is potentially static, linear edges to things. It still doesn't look quite right. There's still something a bit odd going on there. Let me again just have a double check to make sure I've got this where I think I've got it. So I'm checking my to the left of me. So that's top. That's directly west. That's directly east. Directly south. Directly north. Here we've got northwest, northeast, southeast. Oh, David, come on, wake up, man. There we go. And this is what I wanted to capture, is that the YouTube videos are obviously edited and thought about before they're made, and they become quite slick. And I was a bit concerned that people think that that's how they should be programming first time every time. So this little background series introduces the fact that, you know, even somebody that's been doing this as long as I have doesn't get it right all the time. Now that's looking a bit more interesting. Try and get that in. That's quite nice. And it's starting to group things together, so we may want to change the values already. Anyway, the point is that we can change the nature of our morphological kernel and get lots of different effects out of it. I just want to see what happens if I set that to be equal. So before it was giving us an edge detect. I've got a feeling this might do the same. Yes, but it's a much coarser edge detect, and that's probably we're doing too many erosions and dilations in our loop now. But these are the type of operations you would use for object grouping. So here we can see we've got these individual lines on the controls of the synthesizer have now been given expanded boundaries. So this is I can already think of uses for that, because it's easier to plot dungeons and things with lines, but then expanding them into pathways and hallways, etc., becomes more complicated. So there's some nice sort of grouping. Now, this could be also a precursor to other stages of image processing. So I could isolate these individual sections of the image now reasonably easy. I could approximate them with a rectangle and then snip out the original image to do perhaps some character recognition. So it's just about that precursor phase of what are the relevant bits of information you're trying to find in your image. Yeah, that's a very nice example, actually. So the T is retained sort of an approximate T shape, but we've effectively automatically segmented the information in this image in a way that may be easier to process later on. Yes, I guess it's a bit like a bold effect, that's true. So that is erosion and dilation. I probably need to think about how to word that in a concise way to work through it. I'll just comment those out for now, and we'll have a look at the next bit. So let me just set up the drawing out. So we wanted to do input versus output. So in the last video, what did we look at? We looked at thresholding, low-pass temporal filtering, binary operations. I've got the list up here. What else did we do? We didn't do adaptive threshold, sub-L, sharpening or convolution. Oh, we did motion detection, didn't we? That was quite fun. I think now we'll do a median filter, and this one's a little bit more. It's a very simple technique to implement, but requires a bit of thinking about it, and we may have to sort of construct a scene to demonstrate what the median filter is going to do. But let's have a go at implementing the median filter. We don't need to do any of the thresholding. It works on grayscale images, median filter. So I've got my image, captured it, and now we're ready to process it. So the code, as you can see at the moment, is sort of like a shotgun all over the file. I'm just dumping the ideas down, and in the next episode of this, we'll start refining the code into a way that it becomes the final source file I'll include on the GitHub. Let's have a think. So, median filter, what is it? The idea of a median filter is we look at our 8 surrounding neighbours' grayscale values and we store them. And then we sort them to take the median of those values. And the median, of course, is the middle value in the set. It's not an average or anything. We just take the values, we sort them in order, and pick the one that lies in the middle. And that's the value we're going to set our pixel to. So I think, as usual, we're going to want to iterate through our picture. Let me just make sure that the algorithms and everything, just make sure it all loads up before we start. So it should just be capturing a grayscale image on the left. Yeah, and our output was just whatever the first image was. So that's the camera's auto gain coming in. It makes my hand look filthy, doesn't it? But I assure you it's not. Oh, am I doing something to input inadvertently? I don't think I am. I genuinely think, we can probably get rid of that now, we don't need that either. I think that's just my camera's auto gain going, whoa, I'm completely saturated here. Yeah, it's doing some sort of exposure change. If I darken off the image and bring it back out, seems quite excitable. That makes me think then, do I need to add in some sort of manual calibration to these things? Okay, anyway, we can work with this. So, median filter. Yeah, Lucas, I know you don't tend to get into many of the streams, do you? I wouldn't say advanced programmer. Right, so what do we want to do? We want to take our immediate neighbour values and add them to a vector which we're going to sort. Yeah, so we'll not make this performant. One of the things that I get some criticism for on the YouTube comments is, well, you've not done this in a very efficient way because if you're wasting clock cycles by it. And to be honest, I just don't care. What I'd rather do is write the code in a way that somebody reading it can easily understand it. And so easily understanding means not having to think about making sure it's completely optimal. So I'm going to create a vector. We'll just call it v for now, and in that vector I'm going to add in the vector of what, I guess is the key here, a vector of floats, which is going to be the neighbouring pixel values. And so I need to extract those values from the image. And one way I could do that, I could do it manually like I was doing before and just work on a 3x3 area, or I could go out and put in some loops and work on a 5x5 area. So I want to give myself the option of both. So I'm going to put in an additional nested for loop just to scroll around the pixel that I'm currently operating on, and we want to go from one pixel to the left. We'll have to change these names. Let's call them N and M. N and M. N and M. Zoom in a little bit. And I want to go from -1 to +1. I actually want it to include the +1, so I need it to go through 3 stages. So that's going to be for both the X and Y around the pixel that I'm currently looking at. So to just add that pixel value to my vector, v.pushback, and we'll read directly from the input. Input.get, it's my current pixel's location, which is I in the X axis, plus this offset, N. And the same goes for the y-axis, I suppose, plus M. So I'm reading the area around my current pixel value. I'm also including my current pixel value as well. So I want to push back. Why are we getting what's flagging up here? Expected an expression. Have I added something stupid to something stupid? I don't think I have. No, it's just IntelliSense being slow. So now I've got a vector of my surrounding pixel values neighbours, and don't forget the get function that we implemented yesterday has things like boundary checking. So around the boundary we might start to see some artifacts. I agree, sort of nano optimizations aren't that useful. Inside for doesn't give error for I equals 0 status. No, not in this case. As I was just mentioning, because yesterday when we created the get function, where was it? Get here. We actually do this check to make sure that we're within the boundary of the array, or we're just going to return 0. There is another approach you can use in image processing. If you assume that you've got some repetitive spatial frequencies in your image. Now that's the thing about natural images, is you don't ever really know. But sometimes it's a safe assumption to make that your image looks the same beyond the image it's currently looking at. So one thing you could do is start to reflect. So if you went to -1, you actually read the value +1 and -2, and that gives you a nice smooth boundary. Or you could wrap around your image. There's a whole variety of strategies, and it depends on what you want to do. Sevenidus. Thank you for the follow, man. Much appreciated. Right, so image processing, we've now got a vector of our values, and do you know what? Kieran shouted, oh dear me, come on David. Kieran shouted at me yesterday for putting too many brackets in my code. It's just how my brain wants to dump these things on the screen. So just for Kieran, I know he's probably not watching right now, but I'll include that. So we've got a vector, we now need to sort that vector. Now, these are the things I can never remember how to do. So I'm going to pull up the standard library and look for sort. There we go. Sort. And I probably want to throw a small lambda function at it. Oh, has it already got sort of built-in sorting patterns? I wasn't aware of that. Steampunk Devil, thank you very much for the follow. Cheers. Right, so let's do that. What do I need? Algorithm. So I need to include algorithm to do the sort. I don't think. Oh, do I include? I think the Pixel Game Engine actually includes algorithm. So we'll see. See what happens. So standard sort. Let's see what we've got. So we want an iterator for the start, which will be v.begin. An iterator for the end, v.end. And I guess that's our little lambda function. It'd be cool if it does have some built-in things. Standard greater. I'm just going to try that. I've not seen that syntax before, so let's have a look. Standard greater, pass in a float. I guess that's like a pre-made little sorting routine. Oh, we'll see if that works anyway. I did see that a new terminal is going to be released. Yeah, we'll have to see how that affects things like the console game engine. That's I don't really know what the standard begin and standard ends for though. What's that doing that's any better or worse than that? Maybe it could be completely right. So once I've got a sorted vector, I'm going to assume that's sorted. I want to pick the middle value of it to set my pixel to. So output.set. Now the location of this pixel is given by our I and j because that's what we're iterating through the array. I'm already thinking that in the video I might change these to x and y. That's a bit more conventional for people who think about arrays. Image processing tends to use I and j. Just a second, just definitely no more product placement. I think the coffee tastes even better for some reason. That's output I and j. So we've got our value, and now I want to choose the middle value or middle-ish. How many am I going to get out of this? So I'm going to get 9 out of this. So what is my middle value in the median? 1, 2, 3, 4. Yeah, 0, 1, 2, 3, 4. So I want to pick the 4th value out of my vector. And that's median. Median is a strange thing that has lots of practical applications, but has never made sort of any mathematical sense to me as to why it's valid. Gorbit, did you see Magetsub's range-based for loop implementation? I thought that was quite smart. Right, so let's just see what we're going to get out of this. Let's see if we get any errors. And as we start adding more and more features, we will start to see some performance hits. Oh dear, I wish it wouldn't sort of go really dark like that. Let's see if I can do something about that. If I've got the sunlight glaring at the screen right now. So if I close my window, is that going to brighten it up at all? Not really. Oh, it just gets darker and darker. Put my artificial light on. Still looks a bit gloomy. Ah, here's a check actually. Something I want to ask you guys whilst you're watching. I'm currently streaming with night mode enabled on Visual Studio. Sorry, on Windows. Does it look darker and red? I'm now going to disable it. I want you to tell me if there's a change. So has that changed the colour of the stream? So there was no change there. I was curious because I was wondering what it was capturing. Because obviously you think, oh, it's changing, it's getting rid of all of the blue pixel components. But the mouse cursor remains perfectly white on top of this reddish background. That's good to know that it doesn't change. Because I actually prefer working with the night light mode enabled. Anyway, median filter. What are we doing with median filter? So let's find my little test piece. Median filters tend to get rid of what's called salt and pepper noise. Now, yesterday we looked at noise which was a temporal noise. Do you know, I don't like sitting in the dark under artificial light. It's made no difference to the display, so I'm just going to put that back. Salt and pepper noise is sort of sporadic pixel noise. Now this is why I'm thinking I'm going to need a sensible test piece for this. But median filtering has the effect of maintaining most of the image formation. We can see a lot of the detail is still there, but it gets rid of tiny little artifacts. I wonder if I can draw something which might help. Let me get my doodling notebook. I don't know if this is going to be high contrast enough. I'll bring it up to the camera. Oh yeah, see, it's just saturating out. This is interesting. I'll have to have a look at the technical reasons as to why this is going on. I don't think that's very visible, is it? Let me try beefing this up a bit. It is kind of a blur effect, but it's a sort of a single pixel error removal tool. Now, so I'm trying to get with the yeah. I think because my erroneous pixels here, so I've got the high written down quite brightly, and that comes through. But the idea is that these individual little erroneous dots kind of get removed. So you could do this sort of filtering before you do thresholding. The only downside is my erroneous dots are perhaps a little bit too big. One option, of course, is why is the couch going so dark? Right, I need to find a way to stop the auto exposure on this, or at least set it to manual. I find that quite strange. It makes my hand look dreadful. Look at that. Right, I'm going to try. So this is interesting. For the sake of the 8-bit video, I think we've identified, actually, this one's going to be quite difficult to demonstrate. See, I just wanted to sort of not do its auto gain thing. I don't think I can jump into Windows settings very easily and do that. Yeah, I'm not too impressed with the output on that one. Let's just try a slightly larger kernel. So the kernel is the area around the pixel that we've chosen, and we've chosen a 3x3. But if I go to -2 to 3, we're now looking at a 5x5. So I kind of want it to stay as it was. Yeah. Well, with the auto gain doing its thing, these images are becoming... Are they very dark on the stream, or is it just my display? I think they're very dark all around. I don't think there's a way I can jump into Windows settings to set the camera explicitly. See, why can't it just stay like that? Yeah, they're a bit dark. I'll have to do some digging. Well, choosing a larger kernel space, what we can see is we've still got the morphology of the word high, just about, but the erroneous dots have now disappeared. And it's easy to think, oh, well, they've been blurred away into the background. Actually, they haven't. They have been actually removed. Also, the lines of the paper in this case have also been removed. They've not just been blurred away. And that's the effect of the median filter. If I get right up close. I mean, in this instance, what we can see is that the erroneous dots have shrunk considerably in size. And we can get to a point where they just disappear. But the overall structure of the image that we're looking for has remained intact. So we could then go on to do some subsequent processing steps on this noisy data without worrying too much about losing the high frequency components of the image. But we've lost the really high frequency components of the image. I'm going to have a think about why the camera is going so dark, or at least find a way of manually locking that off. I don't think I can do it programmatically via the Escape library. Oh. Right, anyway. So median filters, useful for getting rid of very high frequency detail. Yes, it's a bit like a blur, but it's not quite a blur, because we'll look at blurs next, I think, which is going to be the image convolutions. Now, is that right? Let me just tick off which one of these we've done, so I don't forget. So we've done thresholding, we've done motion detection, we've done erosion and dilation, we've done median filter, and we've done low pass filtering. Temporal filtering. I'm just going to throw a temporal in there. Low pass temporal filtering. Adaptive threshold. Whilst we've got the setup, maybe we can look at adaptive threshold. Yeah, let's have a think about adaptive threshold and see what the effect is. So median filter, we'll check that off. I need to perhaps do a bit of hardware setup, and that's something I can play about with. I'll do that off stream, I think, because I don't want to pull up Windows settings and everything to get all of that working. So what did I say we're going to look at? We're going to look at locally adaptive threshold. Now, fortunately, the code is actually quite similar to the median filter. We've got to do the same kind of process. So I'm going to cut and paste that to start with. But we don't want to sort the vector this time. What we want to do is add up the pixels in that region. So let's change this vector to a float. And we'll call it F-region sum. So when you're working with thresholded images, and if you didn't see the video from yesterday, I'll probably show some thresholded stuff on here. You want to basically choose a value, and if your pixel is greater than that value, you set it to 1, and if it's less than that value, you set it to 0. This time, the threshold we were applying was global. What I want to do now is choose a threshold value which is reasonably local. And that way, if you've got sort of gradients in the image due to lights and shadows and changes in luminance across the image, you've got a slightly more intelligent threshold approach. There is a downside to this though, and we'll see that when we start working with it. So this time I want to accumulate the values of my neighbouring pixels. Region sum. Oh, and the obligatory, as usual, if you've come from the YouTube channel, welcome to my Twitch streams. They're not quite the same. They're a lot more chaotic and a lot less organised. Things go wrong. I create bugs. We don't want to sort anything this time. And also I get sidetracked by what people say in chats. Perfect to hide the wrinkles. Yes, it is. Oh, hey, is she? Good. I've got it for a Sunday afternoon. Got a healthy view account. That is pleasing. Thank you very much. We'll keep that at a 5x5 for now, though we may want to reduce that and see what happens and play with it. And what we're going to do is set the output value based on some function of the sum of my neighbours. In fact, it's the average of my neighbours. So I don't want to. Yes, I want to create that, and I want to work out what the average is. In this case, we've got a 5x5 kernel, so it's the F-region sum divided by 25. Now, we normalise all of our pixel values to the floating point domain as part of the video yesterday. So 25 pixels, what's the average value? And then I'm going to pinch the thresholding code. Let's have a look. Where did we do thresholding? That was the first one we did. There we go. Pinch that in. Now I'm going to abuse the ternary operator again, but instead of input this time, it's going to be our regional sum. And we may want to bias the regional sum. Let's just see what the results look like. So that should be it for... what are we doing? We're doing... completely forgotten the name of it now. Local adaptive thresholding. That's it. Let's have a look. Bring in my high contrast test card again. Where is it? So local adaptive thresholding is I've just chosen something based on the neighbours. We probably need to bias that a little bit better. Make sure I've got this quite right. So I'm going through X and Y. I'm adding up, getting the average of my neighbours, and I'm seeing if... oh no, hang on, that's definitely not right. We want to take the average of our neighbours versus what our input is at that location. Sorry. So get I, j is that if that's greater than the average value of our pixels, then threshold. So it should look quite noisy. There we go. That's a bit better. Local adaptive thresholding. You might be thinking, oh, that's horrific. What do we do? Why is that at all useful? And I'll see if I can find a way of demonstrating why it's useful. Might be, again, a bit tricky since I've not got control over the light. But to my eyes, and it might be difficult for you guys to see, this region of the pad is brighter than this region of the pad. However, our threshold doesn't care. Right, so it's like a high dynamic range threshold. Now, once we've thresholded it, we can go and use the morphological erosion and dilation techniques that we saw earlier to tidy this image up into something that's a lot more useful. So it becomes sort of shadow invariant. In fact, I think you can probably, be a bit difficult to see, you can just about see on this one, I've got going across the word high. The shadow is changing, but the output result doesn't change. So we've got rid of that sort of shadowing effect. You know what I'm going to do? I'm going to try and hack something just to make the image a bit brighter. I'm going to go through all of the input values, and I'm just going to scale them, just so we can see them on the stream for now. I don't want it to affect the image processing output. Input dot set I, j, input dot get I, j times 2. It's probably too much, but we'll see. Draw frame, by the way, will automatically clamp the values if we do saturate them, just to see if that makes things a little bit more visible on screen, whilst I'm fighting the automatic gain. Okay, yeah, that looks a little bit better. The automatic gain really cranks it down, doesn't it? It really changes the exposure. So let's see if I can cast a shadow of some sort. Where's the light coming from? So I wave my arms around. I've got to get both things in shot. So there's the logo. Where's my light coming from? About there. So I'm casting a shadow. Oh, hang on. Let me move that out of the way. I cast a shadow. That's quite an intense shadow now, but it's also a large shadow. I need to sort of get it halfway over each. Let's try putting this light in this location. There we go. Shadow. Right, there we go. Okay, so some of that item is under shadow and some of it isn't, but you can see it makes no difference to the thresholded image, and that's the point that I'm trying to describe. That's called a locally adaptive threshold. Now, the image on the right doesn't look particularly workable, but we can tidy that up with the other binary operations we had before. So we could use, for example, a dilation to fill in all of these individual black pixels, but leave the so it becomes white with black thresholded text on the front. Maybe worth a try. However, it's a cool effect anyway, because it does kind of look like it's a cartoon now, and it can pull up lots of detail the eye can't necessarily see. We can also bias the threshold value. Just catch up with a bit of the chat. Shouldn't I divide by 36? I don't think so. I've got a 5x5 kernel. -2, -1, 0, +1, +2. So I think there's only 25 pixels to choose from. When you use your webcam in your programs, it gets hot. Well, yeah, maybe you're using it too hard. What was I saying? We can also bias what's going on with this region sum. So if I wanted to make it more difficult to choose a pixel, I can of course increase the region sum Let's see, so 1.1. Let's see. So I don't upset my turning operator. Let's have a look at that. And what we can see now is it really sort of starts to highlight detail. There we go. So starting to bias our local adaptive threshold is quite a useful thing too. In this case, we're definitely pulling up the lines on the mat, which are quite distinct. And it's not necessarily the case that a global threshold would be any good, because if I set a threshold value for this mat to try and isolate the white lines versus the grey background, that threshold value may not necessarily apply to something that's really harsh and contrasty, such as the keyboard on the synthesizer here. Very nice, quite like that. Colour it depending on pixel coordinates. In what respect? I mean, surely all you then see is a colour gradient going from top to bottom. Yeah, I quite like that. Make some camera effects for Twitch streamers. Okay, so that is local adaptive threshold. A little bit, again, I'm going to have to think about these. So this is the sort of stuff that I'll play with and then think, well, hang on, is that a sensible one to show? Because is it immediately obvious what's going on? Can I think of some props to make the effect a little bit more visible? Why is it useful? So what was next on our list? So I'm going to leave that in for now because that's a quick hack just to scale the output. Locally adaptive threshold. We'll check that one off the list. So that leaves us now with convolution, blurring, sharpening, and sober edge detection. And I've left these ones for a reason, because you need to know convolution before you can do the others. So again, I need my simple loop to iterate through everything. I need something quite similar again to this one. So I'll just pinch the start of that to work with. Come on, Visual Studio, help me out. So convolution, what is the purpose of convolution? Maybe can, well, my drawing mat's covered in mugs at the moment, so I'm not going to draw that out. But what we're going to do is, for a given pixel, we're going to take a matrix of values and center that matrix on that particular pixel. We multiply all of the neighbors by that matrix, just in place, element by element multiplication, sum them, and that becomes the value of our ultimate pixel. Will I make a normal map of movement? I have no idea what you're asking there, Ishi. Name Thunk, thank you for the follow. There's no motion detection capability in local adaptive thresholding. Yesterday we did motion detection in a very simple way, and there was a way to sort of decipher axis aligned movement quite trivially, but I'm not going to include that in the 8-bits video. I want to get each one of these bits rehearsed and down to about 3 or 4 minutes each. Scorpion, hello. Right, what were we doing? We're doing convolution, and this is sort of an important one. We'll have to think about how we set up convolution. Obviously, I'll probably go to the OneNote and describe, draw out visually what we're going to be doing. But again, do we want a vector? Is that a cheap and easy way to do it? Does it matter in this case? I don't think it matters, does it? What we do need is something called a kernel. And a kernel is going to be a matrix of values. I'm going to use a 3x3 kernel, so I know it's going to hold 9 values. And we'll try and structure this in the code in such a way that it's nice and readable. Get rid of that 9 so we don't start confusing things. Let's just let's just give ourselves a normalized kernel to begin with. So this is just regular kernel, which is 0.0f, 1, 0.0f. And what I hope to demonstrate with this is once you've got a tool which can do kernel convolution on images, there's all sorts of different all sorts of different transforms you can do using the same framework just by changing the kernel values. So what we're going to want to do is create an accumulation again. So this time it's going to be Kernel Sum. And for all of the locations in the kernel, it'd be more interesting perhaps to have a dedicated structure to handle all of these sizes and dimensions so I don't have to keep changing them. F kernel sum is going to be basically it's the dot product between that area of the image and the kernel. So F kernel sum plus equals the input image in that location multiplied by the kernel, also in a corresponding location. So I just have to make sure I get my coordinates right here. So that's m times 3 plus n in this case, because I've got my 1D array and 2D array switch over here. I don't like working with 2D arrays in C++. I just don't like the syntax for it. I need a semicolon there. So that gives us a kernel sum. And that's what we're going to set our output to. I, j, kernel sum. Now, there's some important things we can think about here. It's very easy to saturate your pixel, because if I set all of these values to 1, then on average my pixel value is going to be 9. For example, or 4.5 on average, which is well saturated for the pixel. So it's quite common to normalize the kernel matrix by, well, as you would normalize anything, you look at all of the values, add them up, and then divide the individual values by that. So that way you get a total which is biased towards being within the range of the pixel. So let's have a look. So this should do nothing. What we should see is an input and an output image that look the same, although they'll be different in grade. Oh dear. They don't look the same, do they? What have we done there? Kernel sum equals the values of the pixels multiplied by the kernel in that location. What have I messed up? I've messed something up. So these are the bits that don't make it into the YouTube videos. We did this yesterday with this new triangle filter that we developed. I couldn't do that if I tried. How do you access negative elements of the array? That's a good point, actually. There you are. You see, you've highlighted the negative values of the array. Well done, Ishi. Congratulations. That's what our problem was, I believe. There we go. So that should now centralize to 0 to +2, whereas this one is offset and that's guarded by the get commands. Yeah, I think I don't know how delayed the chat is. I liked the black one. I liked the black one with more black pixels more. I love Twitch chat. Let's just see what that does. Okay, good. They are actually my hands. I really promise they're not that dirty. I don't know why the camera makes them look that bad. What I'm going to do whilst we're doing this, since we're scaling these images to be able to see them, I don't know why the auto gain is not helping me out here. I'm just going to scale the same so they look about right. I'll have a think about sorting that out for the final videos, just so we can see them. Oh, there's definitely no hate on anything to do with the one lone coder. Don't worry about it. These are matrix transformations. You explain these in the Pixel Engine series. If you want a really good video about matrix transformations, the Code It Yourself Asteroids series talks about it from a 2D perspective. And there's also a much more advanced one on the affine transforms, where I talk about the sort of combining the transform matrices into doing something useful. Yeah, my hand doesn't look like that, but the camera seems to think it does. So they're two identical images, and that's of course what we've told it to generate. There's no surprises there. They should be identical, because all we're doing is taking the pixel from our input and copying it to our output. But let's start to play with the kernel here. So if we wanted to blur things, what do we want to do here? We want to take some of our neighbouring values. So if I set these ones to 0.25 and 0.25, I've not got my sums right here. I want to set, let's set this one to 0.5 in the middle, which gives me half to play with. So I actually want to set these to 125, 125. I'm mentally normalizing my kernel here, so that all of the values in here add up to 1. Let's have a look. And so that is a very primitive, well, it might be not that easy to see, but it is actually a blurring kernel. So that has blurred things ever so slightly. I think it's just about possible. Let me bring up my test sample again. Yeah, you can see it looks, once one's in focus, this one's perfectly in focus, this one's got a little bit of blurring to it. And you can repeatedly apply kernels over and over to widen them out, or you could use wider kernels to begin with. But let's actually put in the facility to apply this one several times. I can't use N anymore, I'm running out of letters. A. Let's apply it 5 times. And we'll just have to remember to set wrap this round so we're not always just using the input. We'll set at the start of here, we have this sort of temporary array called activity. We'll set that to be equal to the output, which should be black to begin with. Might need to think this one through. Yeah, I think we need to just prime it with our input. So output equals input to begin with, and then we're going to set activity equals output per loop, and instead of reading from the input, we're going to read from activity. So hopefully, if I've got this right, no promises, what we should be doing is applying this blurring kernel 5 times, and we can see now the image is considerably more blurred. There we go. And of course, if we start to apply it a lot more times, it gets blurrier and blurrier. But it comes at tremendous computational cost. This is a really inefficient way of blurring an image. Quite a nice blur. The structure of the kernel will start to affect what the blur looks like. So we've only got elements in our cardinal directions, north, south, east and west. If we actually included values in our northwest, northeast and diagonal directions in general, we'll get a slightly rounder blurring effect too. So that's blurring. We can also see maybe you get this sort of boundary artifact coming in. So let's really send this. We're going to tank the frame rate now. So we'll set that to some really significant blur. So yeah, the frame rate, I mean, there's so many calculations going on now, it becomes unsustainable. But this is a really big blur. And because we assume that anything beyond the value of the edges of the array was 0, that's why we start to see this black border appear, because the blackness of the beyond the edges of the universe of the image is now being blurred into the image itself. So on the whole, obviously blur is quite destructive. We'll pull that back. And what we'll want to look at, I think, after we've done a blurring kernel, so let's just put that in. We'll record that as a blurring kernel. We wanted to look at sharpening. Now, I have to think about sharpening. I'm trying to remember back to my image processing days. Sharpening was a slightly strange kernel because it had negative coefficients, if I recall correctly. Anyway, what we can do is just play with kernel values and see what happens. So if I want the sum total of my kernel, we'll have to, let's just play with it. You know what, let's have some fun. That's half the fun of this. Let's just hack things together and see what happens. So I don't in any way need to change the loop or the code now. All I'm doing is changing the values in the kernel. And those familiar with Photoshop may have seen this tool. It is actually there in Photoshop, and it's there in most image editing packages. Just have a look, see what this does. So I guess that's kind of sharpened it. It looks like that's done some form of edge detect, but it's not a very nice edge detect. It could be useful, but it's quite common that when you're doing image processing, if you've got an optimized convolution algorithm, you can start doing lots of tricks with combined kernels in a similar way that you can do things like combine matrices in 3D programming. So once you're familiar with convolution, it's a very useful technique to try and do all of the techniques that we did before. I'm just going to set that to 5, just to slightly bias the image. Okay, and that has become a sharpening filter now. So just by changing that number, we've gone from an edge detect to something that sharpens up the edges of the image. And this is exactly what Photoshop is doing when it's doing its sharpening filter. So just by changing the coefficients of the kernel, we're getting lots of different behaviors. So you can see around here along the edges of the mat, it's highlighted them, it's sort of combined them. And before, when we accidentally had that central value at 4, you can see why, because what we saw was these edges, but we were lacking the original image. So by adding that additional 1 to the central component, we're now pulling in more of the original image, as well as how we blend it with its neighborhood. A little bit confusing. I'll have to again try and work on the dialogue for that. And you can take this to extremes. So of course, once you apply a kernel once, we can sharpen a sharpened image. So if I sharpen an image 10 times, it should look like horrible noise. But if you sharpen things loads and loads of times, you can start to see the JPEG artifacts of the camera. Yep, we've completely over sharpened that image. So let's dial that back a bit. Maybe 3 might be enough. Well, I don't think it's. I think it's definitely sharpened it, but it's sharpened it so extreme that it's no use to man nor beast. That is it. Perhaps if we take our original idea of just looking at that particular kernel and applying it a number of times, let's see what we get then. Not much difference. So I think 3 times for sharpening kernel seems to be quite extreme. Let's just try twice. Now, that is quite interesting. I don't know whether you can see it on the Twitch feed, but what I see in my image is everything broken up into lots of little boxes. And that will be the individual JPEG cells, the 8x8 pixel cells that are forming the image. So we're starting to find actual artifacts within the data. It really does enhance that quite nicely. Interesting stuff there. Might be a bit difficult to see on the stream. Okay, but so if we just apply it once and bias it to actually, I mean, we can enhance it. Let's see what happens now. And this is half the fun, just sort of playing with these values and seeing what the effects are that we get out of it. So that makes it look to me so that it's changing the contrast alongside enhancing the edges. It's quite nice actually, I like that one. Makes my hand look less grubby. But it also enhances the noise. So in all of these stages, it's a question of choosing the bits that you need in order to get to the end result, which could be some sort of data that's a bit easier to process with a regular program. Right, so that's a sharpening kernel, what do we say, with a 5 in there. The classic edge detect is Sobel edge detect. And Sobel you can't do with a single kernel. So you need to use 2 kernels and combine them. Let's get rid of our sharpening kernel. So I'm going to put in the first one, which will be Sobel, and I'm going to call it Sobel horizontal. Now, I can't remember if I'm going to get these in the right order, and I can't remember if I'm going to even get the right values, but we'll see. I think Sobel looked something like this. -1, -1 there, 0, 0, 0, +1, +2, +1. Well, we can experiment and see what that does. So if you overall, oh dear, yes, Sobel. Okay, yeah, that's actually, maybe my memory serves me better than I thought it did. So in this instance, we've applied one part of the Sobel edge detect kernel, and it looks like in this case it's detecting vertical edges only. So as I rotate that round, you get a little bit of, during the diagonals, because diagonals contain vertical components, so that's giving us one edge of the shape. Yeah, it's quite nice. I wonder if I've got a slightly more interesting test thing. My hand isn't that useful. I guess it is kind of pulling up the edges of my fingers. So Sobel is a really nice thing. So we've done one half of Sobel. Let's combine it now with the other half of Sobel. Which is a very similar looking kernel, except this time -1, oh sorry, -2, but it's the same kernel but rotated 90 degrees in this instance. 0, 0, 0, and +1, +2, and +1 again. So I will convolve it with the first kernel. I'm just wondering if there's a way I can do this sort of all in one. If I take that and that, double that up. So we're basically convolving the image with the 2 individual kernels. Kernel Sum H. Kernel Sum V. Now, of course, the values of these could potentially go negative depending on the data, and that's something else that we need to consider. So I'm convolving with both kernels, and then I'm going to put the average value of these to the output pixel. F kernel sum V. And I'll just divide that by 2. I think the actual Sobel algorithm, let me just find that for reference actually, because it'll be useful to show. I think the actual Sobel one, it's amazing that I'm trying to get some of this from memory. We'll see. Sobel, let's have a look. Pull that on screen so you can see what I'm looking at. Oh, I did actually remember the kernels. There was a way to combine them. Yeah, okay, they do it using Pythagoras' theorem. There we go. Okay, so I wasn't far off with my kernels. I'm just going to average them, and because I'm just experimenting, let's see what happens. So I've taken them both, got the values, and averaged them. Hopefully we should see fairly uniform edge detect now, but in grayscale. So before we saw edge detection, I missed something out there. This is what I'm saying. So Sobel will give you one edge positive and the other edge negative. And we haven't got the ability to display negative coloured pixels, so I'm just going to set this to be the absolute value. There we go. So that's a grayscale Sibel implementation, which will give you an edge detect. And there's a lot more computation to the Sibel than there was to the binarized morphological edge detect that we found before. Sibel does tend to fail sometimes with diagonals. So harsh diagonals we've got there, because we've not included the ability for it to sort of identify those in the algorithm. There we go, so that's a nice edge detect. But again, all we've done is apply a convolution kernel in an interesting way. It does look like a bump map texture, and it is a perfect way of generating pseudo bump maps. I wonder if we can just quickly abuse something here. Let's just see what happens. If I take that value and divide it by 2, but if I don't take the absolute value, divide it by... I'm going to divide it by 4. I need those brackets. And what I'm going to do is divide it by 4 and then offset it to half. So that way we might be able to see the negative and positive components of the image. Plus 0.5. I'm really just having a guess at this now. I've not sort of thought this one through, but we'll see what happens. Yeah, I don't think I've got the scaling quite right there. Let me think this one through. So that's giving us a big negative component, but it's saturating the white component. I think that might be because we're doubling our output now, that we're just saturating too much. Oh, it's just a... Ah, there we go. That's what I wanted to see. There we go. So yeah, I was just saturating the output. So yes, in a way, it can create sort of pseudo bump maps. It's a nice artificial way. So if you've got a brick texture or something like that, that's potentially one way you could go about creating it artificially. So it looks like it's illuminated. It's false though, right? It doesn't really know anything about the height. You do get sort of softer edges. So if you blurred the image first, you might be able to, as you saw then when the camera went out of focus. Come on. Yeah. Now you get a nice rounder effect, and that might be something to apply. So this is why I'm trying to emphasize, knowing a bit of image processing can really help you out when you're trying to artificially create resources through procedural generation. Is there a way to get the edges smaller? Well, you weren't here at the start of the video, I don't think, Scorpion. We did actually look at one which gives you very precise pixel level edges perfectly around objects using binary morphological operations. I'm not going to repeat that just now, but do check out the VOD. And of course, the final video of this will contain that information. But yes, it's easy to get a perfectly binary edge detect. Oh, do you know what? I'll just show it. Why not? Try and remind myself how it worked. Where was it? It was erosion and dilation. It was this one. So I'm going to upset my program now. So Scorpion, you better hang around. So okay, I think we're done with Sibel anyway, so that's good. I'll just we've done that, and I think we're done with convolution. Oh dear, I pressed the wrong button. Oh, come on, Visual Studio. It's just not working with me today. So we did Sibel. Let's go back to the binarized thresholding activity, which I think was this one. Dilation. I don't think we needed both, did we? We just wanted the this one. Well, we looked at our neighbours and we looked at a specific value of them. I just need to make sure that I've got the image set up appropriately. To begin with, was it that? That's enough, is it? That's in a loop. I can't remember what we did. That's in a loop. Let's just leave that in a loop. And I think we needed to prime the image for this one, didn't we? Yes. I can't remember what configuration we had this set in, so let me just fire it up and hopefully it'll remind me. It does nothing. It does nothing. You broke my program, Scorpion. Why does it do nothing? Because we haven't actually given it a data set to start with. We've not thresholded the original image. There we go. And we're thresholding at 0.2 in this case. There we go. So that's like a perfect single pixel binary edge detect, which we were talking about potential uses for. If you can imagine you generate some nice noisy data or whatever, and you want to create walls in your dungeon or something like that. You can see here, because the camera's changing its gain again, that's why the threshold value is changing. So that's a single pixel edge detect working in sort of the binary domain. So we ditch the grayscale information and just go ahead and work on the binary information post threshold. Right, so let's have a look at my 8-bit list. What have we done? We did blurring and convolution, we did sharpening. I know I've got 9 bits in here, I'd just like to have one more just in case, because some of these may not be that interesting to talk about. I think the median filter might be difficult to demonstrate, although I do actually think it's an interesting effect. So I've now gone through all of the bits that I think I want to include in the video. And I've got some code that demonstrates that the algorithms work. But the code is a complete mess, right? It's all over the shop. It's just my ideas dumped into a file. What I like, though, is that we've done all of this. We've only got about 320 lines of code. So that's a nice starting point. But now it's a case of how do I work on... What I don't want to do in the 8-bits video is go through talking about how we capture from the webcam, how we make the Pixel Game Engine application, but I want it to be visible that when they look at the code, they just go, oh yeah, there's an image and there's an operation being applied to it. And so that will probably be the topic of the next part in this series. I think I'm done for today. So thank you very much, guys. This will be going up on the JavidX9 Extra channel once I'm legally allowed to. And... I think that's it. So thank you very much. Oh, sorry, PhD Jack. It's okay. The VOD will be available straight away. I think it's been a good stream. This one, lots of interesting effects being displayed. So let me just remind you all before you all disappear what this is about. I wanted to do a small document of behind the scenes. How do I go from an idea to creating a video? It's a bit egotistical, but I was doing it for personal reasons that I wanted to just capture that I spend a lot of my time doing exactly this, just hacking code out on a screen, seeing what happens, playing with it, and knocking up the hours, because most of the YouTube videos take 20 to 30 hours to make each. And this is a relatively simple one in comparison. So, thank you very much, guys. Plexum, thank you. Cheers. And I'll see you all later. Take care, everybody.